Hello. So today we will be presenting on GraphX, which is a tool in Apache Spark. So to get started, I'm first going to describe a little bit about Apache Spark to put GraphX in context, as it is part of this larger engine. So what is Apache Spark? It's a key tool that's used in big data and data science today. And what makes it so special is it combines data with machine learning all in one area. So you can do data manipulations and then put that data directly into state-of-the-art algorithms. It also helps with programming machine learning algorithms over multiple clusters as well as other algorithms. It's open source, which is always fantastic. It's probably one of the largest communities in big data today, one of the largest, and it's available in multiple different languages, coding languages. So here's just an example of how Spark could be used. In the top left, we would have like JSON, the raw data. Apache Spark would be used to create a pipeline to directly stream that data into a machine learning algorithm and train that algorithm with that data live. This was important. In doing so, this would skip out storing it in between. And as you must know in computer science, one of the most expensive and time-consuming things to do is to load and store data. So skipping this step cuts down on processing time and speeds up training in general. So that's just one example of how Spark could be used. So some highlights of Apache Spark, we have the batch streaming. So that's basically what I was talking about. Instead of like traditionally you could have data come in and you could go and run it maybe like once a day or certain times, Spark allows you to do it live. So as the data comes, immediately feed it into your algorithm. It has very fast SQL queries on its data in this system. It allows you to do exploratory data analysis. So that would be like your pre-analysis of the data, looking at it in terms of graphs and what's there on very large sets of data. So that's going to be very helpful, as that's also a very complicated thing to do with data sets of that size, as well as scalable machine learning. So being able to run machine learning algorithms on tons of clusters and supplying the methods to go about doing that with fault tolerance. So now we described a little bit about Apache Spark. We can now talk about GraphX, which is a tool in this overall framework used for data science. So GraphX, hence the name, is a tool that can use graphs to go and facilitate different things to the user in Apache Spark. So GraphX is basically a Spark API for graphs and graph parallel computing and how you can go about doing that. It basically supports extract, transform, and load processes, exploratory analysis, and iterative graph computation within a single system. And in it, there's a growing collection of graph algorithms and ways to build graphs supplied to the user. And we'll go in more detail on these through the presentation. So if what I said didn't make too much sense, here's a demonstration of how like GraphX could be used. So we have like the raw data coming in from Wikipedia. And from that raw data, you could go and make a text table with title and body. From that, you could go and create different graphs. So one graph you could do is like the hyperlinks from the Wikipedia. And then you could use a graph algorithm, page ranking, and you get the top 20 pages. So that's all something that like GraphX could facilitate, is that doing that graph algorithm and forming the graph. And again, you could do the same thing with a term document, and then you could use an LDA algorithm to get topics. And then going down the other side of it, we see from the raw Wikipedia, you could go and get like a discussion table. So users and what they've discussed. Then you can look at an editor graph to put them in context, all the users in relation to each other. You can use graph algorithm, community detection to form communities. and you can continue to get more useful data out of that. So this is just one example of using GraphX.
My name is Kemi Ibrahim. I'll be talking about the capabilities of GraphX. So the GraphX package of Spark unifies graph computation, such as the ETL, that means the extract, transform, load. It extract and transform load functionality of data into graph structure. So it can also perform exploratory analysis and also iterative graphs. So this point shows the flexibility of GraphX. GraphX makes it possible to view the same data as graph and also as the collections. GraphX can transform and join graphs with RDDS efficiently, and it can also write custom iterative graph algorithms using the Prigel API. So GraphX extends the Spark RDD by introducing a new graph abstraction, and you can compare GraphX performance to the fastest specialized graph processing systems. So this point is talking about the speed of GraphX. GraphX competes on performance with the fastest graph systems while retaining Spark's flexibility, fault tolerance, and ease of use. So I'll be talking about the set of algorithm that is used in GraphX. We have PageRank. PageRank measures the importance of each vertex in the graph. For instance, when you have a Twitter user that is being followed by many others, the user will be highly ranked. So that means if your page, if an important page is link your page, that makes your page to be more important. And the second one is connected components. So this labels each connected component of the graph with the ID of its lowest numbered vectors. So for instance, in the social network, connected components can approximate clusters. And we have label propagation, we have SVD++, and strongly connected components as well. And the last one, triangle count. So the triangle count determines the number of triangles passing through each vertex. So I will talk about the fundamental operations in GraphX. So we have the structural operator and the join operator. So under the structural operator, we have reverse operator. The reverse operator returns a new graph with all the edge directions being reversed. And we also have the subgraph operator. The subgraph operator can be used in a number of situations to restrict the graph to the vertex or the edge, or to eliminate broken links. And the mask operator constructs a subgraph by returning a graph that contains the vertex and edge and that are also found in the input graph. And the last one under the structural operator is the group edges. The group edges operator merges parallel edges together. Then we have join operator. In this case, we have in many cases it is necessary to join data from external collections with graphs. So we have join vertices and we have outer join vertices in this sub domain here. So the join vertices operator joins the vertex with the input RDD and returns a new graph with the vertex properties obtained by applying the user-defined map function to the result of the join vertices. And we have the last one, which is the outer join vertices. So this behaves similarly to the previous one, which is the join vertices, except that the user-defined map function is applied to all vertices and can change the vertex property type.
We are now going to talk about the usage of GraphX. So as mentioned before, GraphX contains a set of algorithms to simplify analytic tasks. These algorithms are contained in the org.apache.spark.graphx.lib package and can be accessed directly as methods on GraphX via GraphOps. This section will describe the algorithms and how they are used in GraphX. So the main or the first algorithm is PageRank. So it was mentioned before that in the capabilities that PageRank measures the importance of each vertex in a graph. A few examples of this is if a Twitter user is followed by many others, the user will be ranked higher than any other user. Another good example would be the Google search engine. So what made them the #1 search engine is they would display the results, and the ones at the very top, those results were the ones that were the most referenced or linked in other pages. So this became very helpful for users because that meant that results at the very top were the ones that were being the most talked about, and they were talked about because they were probably the most accurate ones, or the ones that contained the most information, and so on. So yeah, thanks to this, Google became the #1 search engine and still is to this day. GraphX comes with static and dynamic implementation of PageRank. So in static one, it runs for a fixed number of iterations, while dynamic, it runs until the ranks converge, meaning it stops changing by more than a specific tolerance. GraphX provides a dataset that can be used to run different algorithms. So they provide users.txt, which is a list of users, and followers.txt, which is a list of the type of relationship between these users. So for example, here in PageRank, we see that we imported the necessary tools that we needed. We load the edge as a graph, the edges as a graph, we run PageRank, we join the ranks with the usernames, and then finally we print the results. And then the next algorithm is connected components. So the connected components algorithm labels each connected component of the graph with the ID of its lowest number vertex. An example would be in a social network, the connected components can approximate clusters. So as we can see here in this example, again, we load the graph as in the PageRank example, the one we saw before. We find the connected components, we join the connected components with the usernames, and then we print the results. I'm just showing you these lines of code to show you how simple it is, but we will go more in depth on a demo later on in the presentation. And finally, we have triangle counting. So GraphX implements a triangle counting algorithm that determines the number of triangles passing through each vertex, providing a measure of clustering. So here again, we import the necessary tools, we load the edges in canonical order, and partition the graph for triangle count. We find a triangle count for each vertex, join the triangle counts with the usernames, and we finally print the results. Now we are going to go on to how to set up GraphX.
In this part of our presentation, I will describe how to install Apache Spark and import the library of GraphX in Apache Spark to work with graph processing. First of all, we need to download the Apache Spark from the following link. So when we go to the following link, we'll see the option to choose the release of Apache Spark. You can also choose which Hadoop version you want to use. So after that, we can download the Apache Spark from the following link. So after downloading Apache Spark, we need to also download the Java JDK. because Apache Spark needs Java JDK installed to work. So we may check that if our system already have Java installed, so we can run Java-version command from our command prompt to see if our system already have Java installed. We can see that my system have already Java version installed. So if you do not have any Java installed in our computer, we can download it from the Oracle website. So this Oracle website, we can download the version of Java JDK for our system like Linux, Mac OS, and Windows. Also, if we want to download previous version of Java, like the current version is Java 18, so we can go to the Java archive folder, and we can see here we can download the previous version of Java. So for Apache Spark to work, we need a Java version which is greater than 8. So after downloading JDK and installing our system, so if we are using Windows, then we need also to download another like file called winutils.exe. So we can download it from the following GitHub link. So when we want to download the winutils.exe file, we also have to check the corresponding Hadoop version. So after downloading all those things, if we are using Windows, then we need to add the path of both the Spark folder that we have downloaded and also the winutils folder where we put the downloaded winutils file. And the path of both of this folder we have to update it on the environment variables and also on the path variables of the system. If we are Linux users, then after downloading the Apache Spark in a folder, we need to update the .bashrc folder. So we need to update this .bashrc file and export the path or provide the path of their folder in the bashrc. And after updating the bashrc file, we need to run the command source bashrc to make that update happen. So when we are updating those path variables in Windows or updating the path in the .bashrc folder in Linux, we are okay to go with running the Apache Spark shell. So to run the Apache Spark shell, we just type spark-shell command from the command prompt. I have already done all the requirement for my Linux system. So just running Apache spark-shell command from here. And now the Spark is running in the command prompt, and I can type any Scala code from here. So now to work with GraphX, we need to import the following libraries in the Spark. Now the GraphX library have been imported. Now we can work with GraphX in this Apache Spark. Here I will provide a demonstration on how to use GraphX to process a small graph. So to show the demonstration, we created a small graph. You can see in the presentation. And this is a graph of various cities, and the edges represents the distance from one city to another. So here in our graph has 5 vertices representing each city. So Detroit, Lansing, Traverse City, Grand Haven, and Houghton. And all the edges from Detroit to Traverse City, the level is 300. So 300 means the distance between the Detroit to Traverse City, and there is a path from Detroit to Traverse City. So we need to know two properties of a graph. So a graph has the vertices. So we can represent a vertex using two tuple. One is the ID of that vertex, and another one is the label, what we call that vertices. Here we can see the vertex Detroit. So it has the vertex ID 1. and its label is marked as Detroit. Similarly, this vertex, it is the ID of this vertex is 3, and its label is traverse. And we can represent each edge by 3 tuple. One is the source, another one is destination, and third one is label. So if we want to represent the this edge, then we have to, this edge goes from Detroit to Traverse City. So the source is label is on, and source ID is on, and destination ID is 3. And this edge is labeled as the number 3, which represents the distance between Detroit and Traverse City. Now I will show how to represent this graph in GraphX. So before using GraphX, we need to actually import the GraphX library. So I will use those commands to import GraphX library in my Apache Spark system. So now my Apache, I have imported the GraphX library in my Spark. So now I want to create the list of vertices that is present in my example graph here. So we can see that our example graph have 5 vertices, and we want to represent each vertices as 2 tuple. One is the ID of that vertex, and another was the label associated with that vertex. So here I created an array of 5 vertices. The first one is the ID of the first vertex, and the second one is the label of that vertices. So, and here L represents the long. So here the ID is a type of long. So we can use like integer type or other types of ID. So here we have 5 vertices, and each vertex have its own ID. So I created an array of vertices, and after that I uses the Spark context parallelize method to use and pass the array of vertices in that parallelized method to create a resilient distributed dataset, which is the default data structure of Apache Spark. So I will show you how to use those vertices. So here I created an array of vertices, and now I need to pass those array into the Spark context. Now the array of vertices that I have created, I passes it to the Spark context parallelize the methods, and this method have been put in the resilient distributed data set of the Spark data structure. And I can see that I can print if our vertex RDD already have all the vertices that I have been specified. So I can use the command called brd.takeOn. So this will print the first element of our array. So we can see that the first element of our array is on comma Detroit. So one is the ID of that vertex, and Detroit is the label of that vertices. So now we have created the list of vertices of our graph. Now we need to create the list of edges that represent in our graph. So we can see that in our graph there are 8 edges that goes from different vertices to vertices. So we know that to represent the edge we need to have specified 3 tuple. One is the source node of that edge, the destination node of that edge, and the distance between those 2 nodes. So here I also created another array where I represent each array element is a 3 tuples. The first one is the source node ID, and second one is the destination node ID, and third one is the distance between that source node and the destination node. So as there are 8 edges in our graph, so I have to create 8 different number of edges in our array list. So after creating that list, we need to pass this number of edges into the Spark context parallelize method into the data structure of RDD. And after passing those things, we can print how the first or second element of that RD. So I will copy this for saving the time of our presentation. So now I created a array list of edges. So now I can use this command to pass those array list into the RDD method. And now I can print the element of that RDD is RDD by using the take method like on or to. So I pass the parameter to here. So it will print the first two element of the edge list. So here you can see the first edge is from node 1 to 3 and the distance is 300. And the second edge is from node 1 to 2 and the distance is 150. So now we have created our vertices and also we have created all the edges of our graph. Also there is another parameter which is the default vertices. So as the syntax have this default vertices, so we need to specify the default vertices also here. So we will create a default vertex and we will put a name to that vertices. Now we have created all the required fields of creating a property graph in Apache Spark as the GraphX library. So now we want to create a property graph. So to create a property graph, we just pass our vertex, list of vertices, list of edges, and our default vertex to the function called graph. So now our property graph has been created and we put a name to our property graph called graph. So if we want to print all the vertices of our property graph, we can do so by just printing all the vertices of our property graph. So now we can see our graph has printed all the vertices with their associated IDs here. So we can also print all the edges that have in our graph. So we can print all the edges. So this prints 8 edges as our graph has 8 edges from one source to another destination node. So now we have created our graph that we have presented for an example demonstration. So to run some operations in our graph, we can use some queries like we want to run some example queries in our graph. So like we are interested to find how many cities and how many roads are available in our graph. So you know that each city represents a vertex of our graph. So we will just run graph.number of vertices. So it will print the number of cities in our graph. So now we can see that the value is 5. So there are total 5 cities in our graph. So if we want to see the number of how many roads there are in our graph. So actually, you know that roads represents the number of edges. So we can print the graph.number of edges. So it will print the number of roads that our graph have. So we can see the output is 8. So there are actually 8 number of roads in our graph. So these are very simple graph queries. We may be interested to run some complex queries of our using our GraphX. So like we are interested to know how many roads have a length of greater than 200 miles. We can see from our graph that this road has the distance of 300 and this road has 250, this road has 220 and this road has 450. So we are interested to know how many roads are greater than 200 miles and also along with their distances. So we can run this query. Here we need to use the filter. So we need to use graph.edges. So it will select all the edges of our created graph. Then we use the function filter. So filter function. Then we will use the case edge. And we know that every edge is represented by source node, destination node, and distance node. Then we will select the when the distance is greater than 200. So this will filter all the source, destination, and distance edges pair that have where the distance value is greater than 200. And we may have multiple such edges. So we will collect the result, and for each result, we will print the output. So we will run this code, and we'll see what it will print. Now we can see this print all the 4 edges or roads that have the distance greater than 200. So now we may interested to have find the more complex queries, like we are interested to find the shortest distance between Detroit and Houghton. So we can see this is the city map with the roads labeled with the distance between them. So we may be interested that what is the shortest path between the city Detroit to the city Houghton. So we can see there are multiple paths that goes from Detroit. So we can use Detroit to Tower City to Houghton, or also we can use Detroit to Grand Haven and then to Houghton. And also we can use from Detroit to Lansing to Houghton. So we can see that each of those roads have labeled with the distances. We can see if we use the following path, then the distance will be 450 plus 250. So total distance will be 700. So if we use this link from Detroit to Tower City to Houghton, so the total distance will be 300 plus 200, which means 500. So if we use this path, from Detroit to Lansing to Houghton, so it will be 150 plus 220. So the total distance will be 370. So this is the shortest path, which is from Detroit to Lansing to the Houghton. So now how we can find this path using the GraphX. So GraphX have a library called shortest paths. So we will import this library to use the library function of shortest path. So now I've imported the library shortest path. Actually, this shortest path library finds all the shortest path from each source node to all other destination nodes. But we are not interested to find all the shortest path from each node to another node. We are only interested to find the shortest path between the Detroit and Houghton. And the ID of Detroit is 1, and the ID of Houghton is 4. So now we will find the shortest path, providing the graph as a parameter, and also the destination is number 4. So here we will run this code. So here we put the parameter graph, and also we pass the parameter 4. So this will create the result will have all the shortest path from all the nodes to the node number 4, which node number 4 is the Houghton. So it will find all the shortest path from all the nodes to the destination Houghton. So, but we will need to find from only the node Detroit to the node Houghton. So we need to use some filtering function to find our expected output. So here we will use the filter function. So we know that our result variable already have all the shortest path that goes from all the nodes to our destination node Houghton. But we only interested to find the shortest path which comes from node number 1, which is called Detroit. So here we will filter our results. That means result.vertices.filter, where the vertex ID equal to 1, because we know that our vertex ID of our Detroit is 1. And then we only need to know about the first path of our destination. So there are multiple paths. So we are only interested to which is the shortest path that goes our destination node 4. Then if there are multiple paths, the multiple shortest path from our source node Detroit to our destination node Houghton. So we need to print all those multiple shortest path using a loop function and print those paths. So now we'll run this function to find the shortest path from Detroit to Houghton. Now we can see this printed the shortest path from node number 1 to our destination node 4. We have to go to from node 1 to 2 and then node number 4. So we can see that number 2 is the node of Lansing. So this is the shortest path from 1 to 2, then from 2 to 4. So which is printed here. So this way we can use multiple queries of our simple graph. So I think we can use more complex queries in future to understand the GraphX tool better. Thank you.
My name is Carl, and I'll be going over some of the pros and cons about GraphX. So what's great about GraphX? The number one thing that's the best feature about GraphX is that it supports distributed processing. And what this kind of entails is that you're able to take on a much larger data set than some of its competitors because you're able to horizontally scale your processing power. So whether you need one machine on your local instance if you're just working on your laptop, or if you're working on some kind of network for a company or a university doing research, you're able to leverage that processing power across many machines of different hardware configurations to be able to crunch very large data sets. This is very useful for like real-time processing as data comes in. Secondly, it is maintained alongside Apache Spark, which is both Apache and community updated. I took a look over the change logs over the last couple of years, and there's been about 7 to 8 updates on average for the last 3 years. Well, Apache GraphX gets updated alongside Apache Spark. Not every update note to Apache Spark has to do about GraphX, but it is very frequent in these 7 updates that 1 or 2 of these release notes are about GraphX. As a third point, there's a large library of pre-built algorithms to use. And why this is useful is because when you're going into GraphX and you're actually building out the code to run, being able to call just one function without needing to write out the code to execute that function really reduces the amount of time it takes to be able to construct something, as well as if I'm a data scientist, I might not have the mathematical or the programmatic skill set to be able to write out some of these functions. So not only does it allow me to write more clean and concise code to review at a later time or to run, but I can also then rely on the expertise of other people that had helped contribute some of these algorithms to the community. So what could be better about GraphX? The number one thing is that it is still an alpha, which, as I'll get to in a bit, means it's kind of limited in a couple ways. While it is still being updated, they do fully acknowledge, this is alpha, and they're both asking the community to contribute towards it, as well as Apache is contributing towards it as well. So with that being said, there is limited API support. While the parent software of Apache Spark has a wide amount of API support, the GraphX library inside of Apache Spark is fairly limited, specifically to the Scala and the Pregel API for syntax. And the reason that's a limitation is a lot of data science is done inside of programs like Python. And while in Python you can use libraries like PySpark to be able to utilize some of the capabilities of Apache Spark, you can't utilize the capabilities of GraphX as it stands today. And as a last thing that could be improved is the ability to optimize and debug the code written inside of your GraphX scripts. It can be a little bit of a tedious process to be able to debug your scripts to just get them to run, but also because it's common to work with such a large data set, trying to tweak some of the code if you are writing yourself and not using these community published functions is tedious. It's not super transparent on the resources being used and how you can make that better. So thank you for taking your time to watch our presentation. If you have any questions, feel free to reach out to our group and we'll happily follow up. Thank you.